Welcome to the lecture series on deep learning in artificial neural networks. This lecture covers the shape of the loss landscape and the optimization methods that are used to find good minima therein. And this specific video presents the questions and aims of this lecture. Remember that in a classification problem, we want to classify the positive examples, such as cars, denoted here as little crosses, from negative examples, from the non-cars, which are denoted here by little circles. We construct such a separating by constructing a separating surface, and this separating surface has to be found by a neural network. And this neural network is a deep network with many layers. We assume that we have a total of m hidden layers. Each layer has n neurons. Then there's also an input layer, the size of which depends on the size of the input vectors, for example, the images of cars. And then there are different possible outputs. We denote the neuronal activity in one of the layers. For example, here, this is the activity, the output of a neuron in layer 2, and this is the first neuron of this layer. And we also discuss the weights, which are the parameters. This is the weights leading up to layer 2, from a previous neuron in layer 1, and this is the first neuron in layer 1. So we'll have many of these parameters. The parameters are the weights and the thresholds, and if you do a simple estimation, you find that the total number of parameters is larger than m-1, where m is the number of hidden layers, times n squared. That would be the count of the total weights. In addition, we have weights from the input, we have weights to the output, and we have all the thresholds. So this can be a large number. Each of the neurons implements a hyperplane. Here, hyperplane in the input space. This hyperplane here is implemented by one of the neurons, and the position of the hyperplane is defined by the weight vector, the set of weights of that specific neuron. So this is one of the hyperplanes. Then there's another neuron implementing another hyperplane. There's neuron number 1 implementing this hyperplane, neuron number 4 implementing this hyperplane. Now, the red neuron up here implements a hyperplane in this space here, but overall, when projected onto the input space, it would correspond already to a nice, smooth, separating surface if I have sigmoidal gain function for these neurons. So the question now is, how do we find the weights? How do we find the position of these hyperplanes, such as the hyperplane of this neuron number 1? Well, we find the hyperplanes, we find the parameters, we find the weights by doing gradient descent on some error function, also called loss function. What I plot here is a one-dimensional sketch, the error function as a function of one of the weights. We have seen there are many, many parameters. So this is really a function of the first weight in the first layer, the second weight in the first layer, and so forth. Somewhere we have the neuron in the nth layer going from neuron K to neuron J, and it continues. So we have a total number of n parameters. So this error function lives in a very high dimensional space. And now we ask the following questions. The first question is, how does this landscape of the error function look like? And we are in high dimension. So such a one-dimensional plot, like the plot down here as a function of a single weight, is it representative? What does this error function look like in high dimensions? And to answer these questions, we give a lower bound on the count of minima that will occur in such a loss landscape. Once we better understand this error function, then we can ask, how can we actually find a good minimum? How can we go down, and we'll use gradient descent, but we will look at variations of gradient descent that use the momentum term, and those that use the Adam optimizer are widely used optimization methods for neural networks. And then I set out by saying we use a deep neural network with many layers. So why do deep networks work so well? What's the difference between deep networks versus shallow networks? And in that context, we also need to discuss the no free lunch theorem. All of the material is standard material that you find in the nice book of Goodfellow et al. On deep learning. There's one point where we go a little bit deeper, and for this we refer to a paper of Brea et al. From 2019.